Today, I'm going to talk about variational autoencoder loss function. At the beginning of my class today, I'm going to give you a brief introduction of variational autoencoder architecture. Then I will derive the loss function. Then at the end, we're going to use this loss function to conduct backpropagation. Backpropagation means updating the model parameters of variational autoencoder. As I explained before, it has encoder-decoder architecture. Encoder is represented by Q, and encoder network, usually CNN type, has model parameter pi. If you have image xi, that's going to be input to the encoder of variational autoencoder. It's going to be encoder. Encoder will convert image information to latent space. Latent space, each image is represented by mu and variance and epsilon. We are assuming that each image has certain Gaussian distribution, and it has average mu and variance sigma. Output of encoder will give us average and mu, and epsilon is a standard normal distribution. Average is equal to 0 and variance is equal to 1. By multiplying this, we can obtain GI. Here we have philosophy that in the G space, we have distribution function. G has many vector elements. Each may have certain value 1, 2, 3, 4, 5, 6. But what we are seeing is that each image has certain average value and variance with the Gaussian distribution. I think this is a unique idea embedded in variational autoencoder. If we convert each images, tiger, lion, cat, or dog, or whatever, if we convert that image information into G space by using the encoder. In the G space, somehow each image has certain Gaussian distribution in terms of numbers. Another meaning is that tiger, cat, dog may have different distributions. Some of this distribution may explain about the tail. Some of them may explain about eye color or number of legs, number of hands, number of fingers. So G might be a certain m-dimension tensor. So in the G space, G function is a kind of continuous function. So we may have certain area where it is the 50% tiger or 50% cat. That's why we can generate new images which may not be present in the real world, but in the G-space, we can create new images, which is 50% tiger, 50% cat. So we can do a lot of generation operation in the G-space. In the real images has large amount of information, a bit amount, but in G-space usually it's one-dimensional. So the number of operations to generate new images is much easier. So we can reduce amount of computation and amount of memory by doing operation in G-space. Now, this latent vector is becoming input to the decoder. Decoder is represented by G, and input is latent vector G, and the model parameter is described by theta. And output will be an image. Input image will be converted into the G-space, and G-space is reconverted to real image Xi by having decoder. Of course, at the decoder, we may have probability distribution like this. And encoder is a kind of CNN type neural network, and decoder is also CNN type neural network. As I mentioned before, one point in the future, transformer network and variational autoencoder will be combined together to make a multimodal generative AI network. Of course, the amount of computation, amount of memory needed for that kind of operation will be extremely large. So amount of computation will increase. Computation, memory, maybe 2030 when we have multimodal generative AI. And in that case, I would say transformer model plus VAE will be combined together to become multimodal variational autoencoder. That's my expectation. Actually, this is a log scale. And you students are working on the HBM design, so probably at around this time, there might be some need to make a true three-dimensional HBM. Right now, the number of interconnection between GPU and HBM is 1024 or 2048. But at that time, the industry will ask us to design a number of interconnection, maybe 10,000 or million numbers. So now, this is the basic architecture of variational autoencoder. Now, what is the goal, target of training? Is determining model parameters of encoder network, and we have to find optimal model parameter of decoder. That is the goal of training. Now, I will spend some minutes with you together to derive equations for loss function. Once we define the loss function, we can apply it to update model parameter theta of decoder and model parameter pi of encoder. Of course, we have to use, once we have this loss function, we can apply gradient descent method to update these model parameters. Probably we have a group of images and we apply it and we got a loss function and we apply the backpropagation to update model parameters. And then we have another set of images we conduct it again and again. We may need millions and billions of images, and number of parameters could be billions and billions numbers, and we have to do repeatedly again and again. And to complete this training of VAE, we are not patient enough. Usually it has to be done in a week or so. If you have some competitor who finished the training in 6 months, they cannot compete to another company who can complete the training process in a week. So that's why I'm saying that computing and memory infra is the main competitive requirement of model development. That is the weakest point of small company, startup company, and universities. So there are another ecosystem where Google, Microsoft, Meta, big company who has big infrastructure and money, they are developing fundamental architecture who can do all this image generation, sound generation, multimodal, and so on. They are doing all the works, and they are releasing those models to small companies and universities. And each small company and university can do some small amount of work that is called fine-tuning to adjust the model for their each purposes. And I think that is the main frame of business model in this world. Now, let's go back to fundamental loss function. At the beginning, I would like to talk about the meaning of this loss function first. G, latent vector, is generated by encoder. Now, G is generated from input image by using encoder. Then G is converted to output Xi, and P theta is the network of decoder, and P is probability distribution. So loss function is we want to minimize entropy of output. And by training decoder model parameter and encoder model parameter. So let's assume that we have output image who has distribution, uniform distribution. The other one is like that. Probability density distribution, probability density distribution, and this could be Xi. 1, 2, 3, 4, 5, and certain number. And number of count for 4 is peak. The other one is negligible. In the case of A, output is very uniform. in terms of color, this is black and white. In terms of color, this is blue, red, and yellow. You remember that entropy of this one is small, entropy of this one is very high. So what I'm meaning is that loss function is defined as entropy of output. We are keep training this encoder and decoder continuously so that output entropy is minimal. And at the beginning of this class, I was talking about many different types of loss function. One of them was mean square error, and another one was entropy. Here we are using the entropy function. So this is overall picture of loss function. We keep training encoder and decoder until we have minimal entropy. We are sending new images and new images continuously. We calculate entropy and we obtain the average entropy. And so once we are able to have some function, so if we apply this function and we know dependency of here, we have two model parameters, decoder model parameter and encoder model parameters. We update the theta and pi until we have minimal loss function. Of course, in order to apply the gradient descent method, we have to be able to clearly define function of this loss entropy with a function of theta and pi. That is a little bit difficult job, but let me continue to talk about that. I'm not sure about the Bayesian rule. What I'm trying to do at this moment is that I would like to, this is the entropy of output images. Now I would like to express that with some encoder-decoder information. We have decoder. If we have xi, gi, the first part is this part. And second part is this part. What does that mean is that if we have some probability distribution, overlap is same. If we go from there or if we come from there. We first have xi distribution. This is conditional probability function saying that with the given xi, G distribution. That is this one. Another expression is that if we have a GI space, this is the probability on the condition of G. So this cross area should be same. That is the Bayesian rule. Because of that, output image entropy is converted to some complicated form. So distribution of output image is changed to latent space distribution. This is a little bit of a mathematical derivation. We are adding same amount at the denominator and numerator. Q encoder function is added at the numerator and denominator. Let's be patient a little bit more. Now we have three terms, number 1, number 2, and number 3. I will explain that one by one. Let me to explain from the beginning again. After we determine the VAE architecture, it is composed of encoder, decoder, and the latent space. In the latent space, each latent vector has Gaussian distribution. Now, I want to define the loss function. Loss function is basically entropy of output image. We want to train encoder and decoder so that we want to minimize the entropy of output function. That means, let's assume we have output distribution A and B. B is what we want, more discriminative. Average or uniform distribution is not preferable for loss function or output. We want to make entropy as small as possible. So now entropy is minus. It is amount of 2-bit information to describe this digital output distribution. If we can describe this output with a single digit, that is very good. That is the lowest bit number. That is lower entropy. If we need billions of bits to describe this distribution or this probability distribution, then entropy will be higher and higher, almost like infinite. Let's forget about this derivation process, but output image entropy is converted to this function. In the statistics theory, we have this kind of Bayesian rule and this kind of operation. Let's talk about first term. With the given Gaussian distribution G space, we can obtain output image with decoder parameter theta. That is the first term. How can we obtain this term? I told you that G is a kind of Gaussian distribution. This is G1, G2, G3, Gn. In each image, we have many different G can be sampled from the Gaussian distribution. And for each G, we can apply it to decoder and we obtain the output and we measure the entropy. And if we have 1,000 different sampling, we can have 1,000 measurement using the decoder, and by dividing that by number 1,000, we can obtain average encoder. So this operation is only for decoder training. In this initial function, encoder and decoder is combined together to make an output. So it is very difficult to train encoder and decoder separately, together. So this first meaning is that this first term can be used for decoder training. Because on the given latent space, we are measuring the entropy of output image. So by having this mathematical operation, we can separate loss function of encoder and decoder. Second, first term is with a given image xi, we generate Gaussian distribution. This is actually Gaussian. And P theta E is, we assume standard normal distribution of Gaussian. Standard normal distribution means average is equal to 0 and variance is 1. That means in the target, it is a kind of center position. So this second term can be used for training of encoder. By having this mathematical operation, we can split encoder loss function, decoder loss function, and encoder loss function. And I'm assuming this Gaussian distribution is standard normal distribution, and this is what is the output of encoder. By having this, comparing this entropy is called KL divergence. They are comparing the entropy of these two functions, and we are training encoder so that this encoder output is becoming as close as possible to the standard normal distribution of Gaussian. So this term is called as the regulation loss term. By having this second term, we are enforcing that the output of encoder should be Gaussian. Why? Mathematically, it is easier. By having Gaussian function, there are many easy equations to represent this KL divergence. Gaussian, by comparing them in entropy space, it is easy. There are many easy equations. Numerically, it is very easy. I don't know, our reality is easy. Myself is Gaussian. From 9 o'clock to in the evening, my mood might be Gaussian. I don't know, happy and unhappy, happy and unhappy. This is high entropy. But there are 90% of the time we have happiness and unhappiness are combined together. This is high entropy. But variational autoencoder want to have very low entropy. We have third term. If this is encoder and this is decoder, this term is coming from this direction, from input image to latent space, and second term is from output image to latent space. With the given input image, we have to calculate latent space. That's actually Gaussian. And this is the another reverse way of decoder. And we have output image, we want to calculate latent. And we are assuming it's becoming 0. Because we designed the CNN type encoder, we know the output, but we don't know reverse direction of decoder. But we assume that it's the same. Another philosophy hidden here is that we can generate latent space from encoder. The other direction to obtain G is reverse direction of decoder. But encoder is the positive direction. We don't know what is going to be backward direction. And we are assuming at this moment, these two latent vector is equal to 0. So we have basically two loss functions. First one is the construction error. We call it the construction loss. And second term is regulations. In the next class, I want to continue my class to talk about diffusion, stable diffusion model. That will be a little bit more difficult. But at the beginning, you may be having a hard time to understand this, but it is, and it works very well. Thank you for your attention.